All right, this is the final video before we start doing limits. The title of this video could be, "Oh my God, I hope you didn't forget anything." But realistically, it's called "Some Functions You Should Know." If you don't know any of these, or if you don't know any of them, come see me. If you don't know or don't remember some of these, I have some videos out there. A lot of this is stuff from pre-calc, so you can go back and watch the videos, or you can talk to me and we can figure out how to get you to sort of know these better. But basically, these are some things you should know. So polynomials, right? These are the first functions you learn, right? Because they're the basic building blocks for almost every other function. In fact, you're going to see something in Calc 2, if you make it there, that basically says all functions secretly are polynomials, sort of. And that's pretty amazing stuff. But basic polynomials look like things like 3x squared minus 5 or x cubed plus 5x minus 7. The degree of a polynomial is the largest power on a variable, right? So x squared is the largest power in 3x squared minus 5, so the degree is 2. The reason you need to know the word degree comes up in a few lines here, but polynomials, they're the nicest functions. They're continuous, right? You can draw them without picking up your pen. They're defined everywhere. They're smooth. They don't have any jagged edges. They don't have any pinch points. They're nice. They're really nice functions. Polynomials have, at most, the degree number of roots. So a quadratic can't have more than 2 roots. A cubic can't have more than 3 roots. And they have, at most, one less than the degree number of turning points. So a quadratic, I'm sure you know what it looks like. It looks like an umbrella, or it looks like a cup. And it has at most one turning point. In fact, it has exactly one turning point. Polynomials don't have asymptotes. And as you let x get really big, they have to go to plus or minus infinity. They don't level out. They escape. So that's polynomials. Again, they're the most basic. They're really important. And here's the first place they're used. Rational functions. Rational functions are the ratios of polynomials, right? So a rational function could look like something like x over x squared plus 1, right? They are continuous as long as they're defined, right? There's plenty of places they're not defined, but wherever they're defined, they're continuous. They're smooth everywhere they're defined. Polynomials, rational functions also don't have pinch points. They are defined anytime the denominator isn't 0. So anytime you see a problem, it's usually because the denominator is 0. They have, at most, the degree of the numerator number of roots. So the roots only happen when the top is 0. And that makes sense, right? Because a fraction can only be 0 if the numerator is 0. They have horizontal or vertical asymptotes sometimes. You can see the picture I drew here has both horizontal and vertical asymptotes. And whatever happens out by infinity on the left is going to be very similar to what happens out by infinity on the right, which is to say, if one side has a horizontal asymptote, the other side will also have a horizontal asymptote. And if one side doesn't have a horizontal asymptote, the other side can't have a horizontal asymptote. That's what I mean by similar. So those are rational functions. Nth roots. So, right, nth roots are things like the square root of x, or the cube root of x, or the 7th root of x, or the 4th root of x, or all these roots. So nth roots are also continuous. These may not be smooth. There may be pinch points depending on what it is your root looks like. But odd roots are defined everywhere the radicand is defined, and the radicand is the stuff inside. Like if you look up top, x plus 5, and x squared plus 3 are the radicands. right? Because they're what's under the radical sign. And even roots are defined everywhere the radicand is positive or 0. I should have wrote or 0. So as long as, in fact, that's going to bother me if I don't, or 0. So square roots, you can't take the square root of a negative number. You also can't take the 4th root of a negative number, or the 6th root of a negative number, or the 108th root of a negative number. You can take the cube root of a negative number, right? Because 3 negatives make a negative still, so that's okay. And roots only have zeros whenever the radicand is 0. So if you look down at the graph below, the square root of x plus 1 is 0 when x is negative 1, because negative 1 plus 1 is 0, and the square root of 0 is 0. The cube root of x minus 1 is 0 when x is 1, because 1 minus 1 is 0, and the cube root of 0 is 0. So there's a couple of graphs down below. You can see that the red graph stops because if you try to plug in the x values to the left of where it stops, the radicand, the part under the radical, gets to be negative, and that's not okay. So trigonometric functions, right? Sine, cosine, tangent, secant, cosecant, cotangent, blah, 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 blah. All these trigonometric functions, right? Sine and cosine are the nicest. They're continuous. They're smooth everywhere. They have period 2 pi. They have minimum value -1 and maximum value +1. That red graph on the bottom is what you need to think of when you're thinking of sine and cosine. The orange graph down below is tangent and cotangent. They're continuous whenever the sine or cosine is not 0. Right? Tangent needs cosine not to be 0. Cotangent needs sine not to be 0 because tangent is sine over cosine. So if cosine is 0, that's bad. They have period pi. They happen a little bit faster. And they can make anything, right? Where sine and cosine can't make anything bigger than 1 or smaller than -1, tangent and cotangent can make all values. Secant and cosecant, secant's 1 over cosine and cosecant is 1 over sine. So they have problems. Secant has a problem when cosine is 0. Cosecant has a problem when sine is 0, right? And so, however, secant and cosecant are continuous. They're smooth everywhere. They don't have their problems. They still have a period of 2 pi, and they're never between -1 and 1, right? So if you look at the graph of secant and cosecant down below, that shows you that they never get close to 0, right? They always sort of swoop away. Exponential functions, these are things like 2 to the x, right? 1/7 to the x, 1/3 e to the x minus 5, all this stuff. These are all exponential functions. Some base to the power of x is an exponential function. And if you add 1 to the exponent, it's the same as multiplying by the base. So the difference between 2 to the x and 2 to the x plus 1 is that 2 to the x plus 1 is 2 times bigger than 2 to the x. It's like multiplying 2 to the x by 2. Exponentials are nice because they're smooth and continuous. They're always either increasing. If you look down below at the graphs, the red one is always getting bigger as you go to the right, and the brown one is always getting smaller as you go to the right. They either always get bigger or always get smaller. They never do any turning around like a polynomial. They also have a horizontal asymptote, and unlike the rational functions, their horizontal asymptote only happens on one side. Right? We said with rational functions, if one side has a horizontal asymptote, the other side has one. Here, it has it only in one direction, either out to the left or out to the right, but not both. And the exponential function doesn't have any roots. There's no value of x, so that 2 to the x is 0. So that's exponential functions. And the inverse of exponential is logarithm, and the logarithms look like things like log base 2 of x or ln of x, right? And remember, ln is log base e. They are the inverse to the exponential functions. And if you If you go back to the other video where I talk about what an inverse is, or you go back and you watch my video on logarithms and you refresh yourself about that, the whole point in an inverse is that instead of writing logarithm, you could write it as an exponential. And so log base a of x equals b is the same as x equals a to the b. Logarithms are like exponential functions in that they're continuous for positive inputs. Right? So log base 2 of x, you can put in any positive number for x, and that's fine. You can't put in negative numbers. You can't put in 0. Right? You can't put in 0 because 2 to the x can't be 0. Remember, with inverses, you can't plug into an inverse what you can't make for the original function. So they're continuous for positive inputs. They're smooth. They have a root when x is 1. They have an input when they have an asymptote, a vertical asymptote when x is 0. And so these are the basic functions. These are the things that you should have built up at some point and that you should be coming to this class understanding. If you don't, if you're missing any of this, please go watch some more. Go look at my videos from pre-calculus. They cover trig and exponentials and logarithms. Refresh yourself. Make sure you understand these. We're going to use them a lot this semester. That's it. So go ahead, answer the questions, take the quiz on Desire to Learn, and then I will see you in class.